All right, so we're in section 4.2. In the previous section, we were looking at the concept of a maximum and minimum, both algebraically and graphically. Now we're going to be looking at the concept of an inflection point. So a point at which the graph of a function f changes concavity is called an inflection point. Okay, so an inflection point is where the graph changes concavity. So we saw the max and the min values were where the graph went from increasing to decreasing or decreasing to increasing, right? Where the first derivative was changing sign from positive to negative or negative to positive. Well, the inflection points are the same type of thing, but now for concavity, so for the second derivative. So suppose f double prime is defined on both sides of a point P if f double prime of P equals 0 or f prime of P is undefined, then P is a possible inflection point. Okay? We still need to determine, is it actually an inflection point or does it just go from, concave up to concave up again? So to test whether P is an inflection point, check whether f double prime changes sign at P. If it changes sign, that means we went from concave up to down or down to up. And that's what makes an inflection point. So let me get a couple graphs on here. So here's a graph like that, and then one that looks kind of like this. So the point in question would be right around the middle, somewhere in here. Same thing on this one. Okay, so that would be P. So that's P. Shrink this back down. Okay, so there's our point P. Now in this first graph, notice the graph over here on the left-hand side. This graph is concave up. All right, so this is concave up. So f double prime of x is greater than 0. And then by the time we get to this side of P, the graph is now concave down. So f double prime of x is less than 0. Okay, so since we switch from concave up to concave down, we have P is an inflection point. Okay, so this is where, so right here, this is where f double prime of P equals 0. And this is our inflection point. Also abbreviated IP is our inflection point. Similarly, if we have a graph over here, this is going from concave down, so f double prime is negative, to concave up, so f double prime is positive. There we go, concave down to up. That means that P, in this case, is also considered an inflection point, right? So f double prime of P equals 0. This is an inflection point as well. Okay, we could have cases where we go concave up, and then it levels off the concavity, and then it just continues going up, right? In that case, that would not be an inflection point. It actually has to change concavity in order for it to be an inflection point. So let's go back to our favorite function here, one we've been working with since the last section, and let's determine any inflection points for this function. So we have already found the second derivative of this function, so you can go back and refer to the previous times that we did this problem to look for that. So we have found, so we already know f double prime of x is 6x minus 18. Now to find where the inflection points are, I need to find where f double prime, that second derivative, is equal to 0. So we're going to set this equal to 0. You'll notice this looks similar to the first derivative test for maxes and mins, and the process is nearly identical. But right now we're working with the second derivative because second derivative and inflection points always go together. Okay? Inflection points are talking about concavity. So if we solve this, then we get 6x equals 18, so x equals 3. Now, this is a possible inflection point, so make that a note. So this is a possible inflection point, but we still need to test it. So what we're going to do to test it is we're going to set up a number line, put our possible inflection point on there, and we're going to check a point to the left and to the right and see if the graph changes concavity. So we can pick any points we want, so I'll go ahead and do f double prime of 2 and f double prime of 4. If we plug in 2, we get out 12 minus 18, so that's negative. And we plug in 4, we end up getting out a positive. So this goes from concave down to concave up, which means that because it does change concavity, it is an inflection point. Okay, so since f went from concave down to concave up, f has an inflection point. At x equals 3. Okay. And if we go back and look at the graph on Desmos, you can see right here. So let's get the original graph back on here. That's x cubed minus 9x squared minus 48x plus 52. All right, so again, our very compact graph. Let me just modify our scale here a little bit. X-axis, go from negative 10 to 10, 15, that's better. There we go. Now we can see this a little better because the scale is shifted. But notice, again, this point up here, that was our local max, right? Our negative 2, 104. There's our local min, the 8, negative 396. The inflection point, we said, was at x equals 3. So that would be right there. And if you plug that into the original function, you'll find that you do get the point 3, negative 146. So let's just plot that really quickly. So that's 3, negative 146. So this is our inflection point. All right. And that's the only example that we're going to be doing with inflection points at this time. We will be looking more at all of these concepts, kind of bringing them all together in the last couple sections of this chapter. But just a nice quick section for section 4.2. Now we have a lot of the tools that we need in order to start looking at these graphs. There's one more that we're going to really flesh out in section 4.3. And then we're going to be pretty close to finishing up this chapter.